Yeah, I was when preparing the talk, I was kind of balancing between making it more conceptual, and finally I diverted into the completely opposite direction and decided to make it very, very methodological. Okay, so the things I've been talking about, I published in these two papers, or the common field, the common knowledge in the field of non-invasive electrophysiology. Because I didn't mention, I'm, I'm the director of the Center for Magnetic Interfaces, and we do quite a bit of projects. And I try to systematically present them somehow, and this resulted into such a interesting tree diagram. So I will be talking to you today about neurovisualization, magnetoencephalography, and functional networks. Okay, so only this little branch, and of course, this is performed. The work is performed by a by a group of great scientists, great students, and great PhD students. Um, but I will just mention a very small aspect of it. Okay, so the school is very clearly dedicated to network neuroscience. Okay, okay. Okay, so the school is dedicated to network neuroscience, and in non-invasive neuroscience, what we were doing, we usually use EEG, electroencephalography, magnetoencephalography for the measurements of brain activity. When we talk about networks, we usually go from the brain activity to the sources, to the activity of sources, and then the second step we go to the networks. We basically extract the time series of sources and then try to see how well they're coupled. I will talk about this in details later, but how infer some statistical measures of coupling between the time series of the sources, and then we make inference about networks. Okay, so what we are developing in our center is the network-centered approach for converting the observed data, and so we are trying to avoid the second step. Okay, I will show you how it's possible to do this and to embed this whole thing, not embed into the sample sheet or submerged to, but embed this network estimation task into and represent it as a linear estimation problem, which basically allows for introducing priors and enjoy other interesting tricks that we developed in the field. Okay, so the brain is mapped with a lot of different functional brain imaging modalities, and I am primarily talking about magnetoencephalography that enjoys to be very close to the sweet spot of the ideal spatial temporal resolution, and MEG can be characterized by about several milliseconds of temporal resolution and about 5 millimeters of temporal, 5 meters of spatial resolution, meaning that you can resolve, you can see that sources are different, and those sources can be as close as 5 millimeters of each other. And there are studies actually that show that you can even resolve up to like 1 or 2 millimeters, but for this you have to be focusing on sources that are located in the regions of high curvature of the cortex. Okay, and that okay. So the neurophysiological signal origin. Okay, the big picture. We first start assuming that we have direct access to the data. Okay, we have direct measurements of neuronal activity, of the activity of some relatively large but spatially confined functionally how to say, uniform population of neurons. Okay, so the legend in neurophysiology is that the signals we measure basically come from the postsynaptic potentials that occur in the dendrite of the neurons as a result of the presynaptic potential impingement on this dendrite. Okay, and the reason we see signals non-invasively is because we have those very long apical dendrites, which are long, and also we have a bunch of neurons that receive more or less coherent input, coherent in time, so that the whole bundle of these neurons, the cerebral cells, get current propagating them, and we can approximate this current with current dipole. Okay, and this current dipole is actually what we see. Its activity is what we see, and the current dipole is not actually present in the brain. Sometimes people ask, do current dipoles are present? Are current dipoles present in the brain? No, they're not present. But current dipoles are formed by these dendrites, and we are approximating this highly dense dendrite tree receiving coherent in time input at the current vector. Okay, but this is a very nice and simple electromagnetic model of what current dipole allows for nice modeling, so the nurse problem and stuff. Okay, so and we assume now during the first 1/3 of the talk, we assume that we have access directly to the activity of specific brain location, and in this picture from this nature paper by J. Kenny Miller, is showing the electrophysiological signal, and Abadai will be talking about magnetoencephalographic signal later, where we have sensors located around the head. But for this moment, we only speak about the activity, assuming that we can measure it at specific brain location. Okay, so this is like basic stuff, but it's important. Okay, and since this is a school and this is not just a talk, so I decided that I will submerge you into all this. Okay, so please, if you have questions, do ask them, but ask them very loudly. Okay, because there's noise here, and my left ear is not here. Okay, so anyway, when we talk about neurophysiological signal, in the classical electrophysiological experiments, we distinguish between 3 types of activity: spontaneous oscillations, evoked response, and induced response. Okay, so first think about the spontaneous oscillations. Well, spontaneous oscillations is the type of activity that occurs without any external stimuli, for example, and results from the coherent activity of the neurons, which tend to fire at certain time, for instance, with some jitter, of course, and then tend to be silent. That could tend to fire, then tend to be silent. The origin of these oscillations is very complex. It can come from thalamocortical interaction. It can be other sources. I'm not talking about this now. I'm just stating that if we attach the electrode to a specific region of the cortex and reference it to some other location, we will be able to see something like this. Okay, and these oscillations, what we observe, we can classify them to belong to different bands, to like alpha band and alpha oscillation. Most of you know, right? When you close your eyes, for instance, in the occipital region, we see alpha bursts going on, and the alpha oscillations coming to bursts of activity, and the oscillation itself is well characterized by the envelope, which is basically instantaneous amplitude of this oscillation. Okay, or so think about this. Of course, there are other bands like beta, and delta, and not to say that oscillations are the best model, no, but it's a ubiquitous model. Okay, it's very widely used in neuroscience. Now it's been questioned whether or not we really can describe the activity of oscillations, but in some cases, or in most cases, it is the case. Therefore, we focus on this. Okay, so and also there's very interesting space frequency relationship when the brain is a dynamical system. If you talk about the low frequency oscillations like alpha band, for instance, that when, for instance, you do some motor tasks, the desynchronization, the drop of amplitude occurs over a very large brain area. When we talk about beta, the desynchronization occurs in a relatively small area. This is our data measured with this invasive grids with 3 mm spacing between the electrodes. Okay, but this is just to show that it's not hopeless to be able to measure these oscillations with NEG or with EG, because resolution of about several spatial about several millimeters. Basically, if we talk about alpha and beta oscillations and even gamma, it is possible to quite nicely pinpoint the spatial origin. Okay, so then evoked response is another working force of human electrophysiology, usually human electrophysiology. It basically lies in presenting to the subject. It occurs when you present to the subject a stimuli, like for instance, certain images or certain sounds or tactile simulation, whatever. Those errors, those simulations, and you get some response. Okay, this response here is highly variable, as you can see, but inside of it, there's something like this here, okay, which peaks at very early time and then has other peaks later. And these early peaks usually correspond to some primary sensory processing, the processing of the primary sensory areas. and subsequent peaks are usually generated by the activity of more complex hierarchical structures. Okay, and so in order to highlight this guy, we usually align these responses with respect to stimulus time like this, and average to get this picture. Okay? Also, sometimes draw the variances here, show that what is the variance, and then based on how high the peak is with respect as compared to the variance, you can say that this is significant or not. Right? Okay, this is all needed because my goal is to first show you how we image the brain when we just talk about surfaces, and then talk to you about networks and show that you can do networks in the same way you do surfaces. Okay, that's why I'm this more or less limited stuff. Okay. All right. So and then there is induced response. Induced response is an interesting creature. Okay. The first of all, that evoked response is actually very deep. Evoked response with respect to the rest of the activity is usually about 10% or even less. If you talk about alpha, beta, data bands. Okay, so therefore there's another activity that's induced by the stimulus. Okay, so the black one is the evoked response, sure you know about, right? And the red one here is the induced response. Okay, the characteristic of the induced response is that its power increases as a result of the stimulus. Okay, but its phase is random with respect to the stimulus. So unlike the evoked response that's phase locked to the stimulus, which allows for nice averaging and emphasizing it after the coherent averaging, the induced response, if you average, will die off. Okay, because the phase is different every time. Okay, so in order to see it, you have to actually go into the squares, right? And usually induced response is observed in the so-called time frequency domain. We'll talk about it later in more details, but here you can see a very nice picture of actually the Tibet wearing OTM, optical Doppler energy sensor, and imagine the movements of his hand, and then relaxing. So here this is the kind that he's imagining. You see synchronization of the alpha and beta components of the sensory motor inputs, and then when he stops and stops resting, you see the rebound of this. This is one that is a single sensor type. This is fantastic. Single energy sensor, right? Something create nothing. All right. So the induced response is an important guy because we will be primarily focused on looking at the connectivity patterns that are exhibited by this induced response. If we talk about stimulus-based environment. Okay. Do you have any questions? No, everything is clear. Good. I did a good job listening. Okay. So now another little piece of information, very simple signal processing concept that we all need in the first slides. Okay, so when we talk about harmonic signals, we usually, as I mentioned, we characterize the harmonic signal by the envelope, by the magnitude or amplitude, right here, right? So amplitude is always constant, and also phase, right? What is phase? Well, phase you can think this is if you're show here. Phase, if you consider the signal to be if you consider a signal a counterpart of the signal of the harmonic signal, that you add the sign to this guy, right? Then we represent this oscillation as a rotating vector in the imaginary plane, in the complex plane, and then this angle is basically the phase of the signal. Okay, and the phase is important because exactly the coincidence of the phases and maintaining of the phase difference between the activity of two populations of neurons is a hallmark of their talking to each other. We'll go into more details, but to get access to the phase, we do very simple things. So you all know that the Fourier domain representation of the oscillation leads to that, right? I put the continuous, therefore continuous signals, therefore there are delta functions here. And then how to make a real metric counterpart for you so that you get access to the phase and to the amplitude, to the amplitude. Well, it's very simple. You just remove this guy. Okay, you just remove this guy, and in order to keep the power, you multiply this guy by factor of 2, because they split the power, right? So you multiply by factor of 2, and then if you do the inverse Fourier transform, it's quite clear that this integral this integral will let this guy who will remove the imaginary component, right? And this integral will only see the complex exponent located at f0, right? So just to right? Yeah, so that, and then your x of t, that means your complex signal, which will be known as capital X, okay, will be characterized by two curves. The first, the blue curve, is your original signal, and the red curve is complex component. The whole thing is called analytic signal, and this operation is called Hilbert transform. Okay, so you can represent Hilbert transform differently through the integral, which you can derive it, but it's still comprehensible because it's unclear what it's doing. But this is actually how Hilbert transform is so, but once you have the access to these two guys, you can sum the real and imaginary parts, raise them to the square, and you can get the amplitude of the time series, and you can of course extract the phase as arctan of the ratio of imaginary parts. Okay, so here's this picture of the oscillation of rotating thing. If you expand this, because we never have pure harmonics, right? If you expand the thing, you consider so-called event processes where the energy is centered around some frequency, but the spread is relatively small as compared to the distance from the origin to the frequency itself. That you get something like this, right? And the model is that amplitude modulations, amplitude modulates the cosine, and actually this amplitude is spread in the spectrum. This variation of this amplitude is spread in the spectrum, and the spread of the spectrum may occur not only because of variation of amplitude, but also because of variation of phases. And we will see this is important. The variation, the fluctuations in phases is and alignment of this phase here between two populations is the hallmark of the two populations communicating with each other. Okay, so the same thing here. You do this. You can extract phase, right? And then in case of broadband networks, it's not any longer a socle, but some curve, where each time instance, the length of this vector is your instantaneous. All right. So now that was very brief intro, and I hope everything is clear, right? So now and you can keep questions if you're shy to ask them questions now. You can keep them by the end of the talk when you're less shy, sure. Or you can ask for 3 days in here, and we can discuss. Okay, so well, you're already convinced that the networks is the essence, okay, of the brain activity or brain work. Okay, so and these networks are necessary because brain consists of, like, if you talk about some functional specialization of brain areas, the actual specialization on the tasks are irrelevant to our usual behaviors and spectral behavior. Okay, so in order to generate the behavior, these brain regions need to communicate to each other, not to perform so-called functional integration, in order to result in our thoughts, in our movements, and whatever. Okay, and this synchronization is one of the hypotheses how it occurs. It occurs through synchronization of the activity of different populations. Okay, so Pascal Fries published a very nice paper which summarized the results of many studies, and he put forward this communication via synchronization hypothesis that if you have 3 populations of neurons and one population can emit a series of spikes, these spikes are going to be perceived only by the population that is in the active state, that is capable of perceiving this, right? And this is usually the active state is usually characterized by the specific phase of the neuronal oscillation. If we talk about not-based measures, because again, when we do synchronous phase, we usually focus on oscillations, not just separate spikes, because we just don't see it. Okay, and the other population, which is idle, which is not active, which is not capable of acting now, is not perceiving the activity from the first back, from the right back. Okay, and this way you implement the spatially selected functional networks, and also the sensitivity changes over time, and therefore networks that I think time okay, so this is more or less clear. Well, to be honest, it can be criticized, okay, but in order to do something first, in order to some work, you still have to pick some constraints. Okay, let's assume that we believe that but first of all we have to believe the legend of the origin of the MEG, and right, well, more or less believe it, then we have to believe in this, right? And when we believe in it, because largely it makes it sounds like also we can do our research and we can deviate around it, and maybe later on develop some more plausible hypotheses. Okay, so therefore it's important not to do the work rather than to sit on the couch and do inferences. Not to do something, you need to stand on some stones, right? And build other stones. Okay, so all right, so as already several times mentioned to you, that the coupling between neurons and neuronal relations is reflected in the phase of the activity. One couplet, and again, we are talking here about only one small aspect how the networks can couple to each other, how the relations. We talk about the frequency coupling, okay? Because there are other types of coupling, like for instance, it's known that slow oscillations get high frequency coupling, right? For instance, as I said earlier, the gamma oscillations occur only in the specific phase of alpha, for instance, of beta oscillation. Okay, so those across frequency coupling which are not mentioned today at all. Okay, it is not linear coupling. So here we're talking about linear coupling because we're going to connect these with a linear method for solving the first problem when we switch from the ideal world we are now in and have access to each relation directly. Okay, so and then if you look at this data and if you compute the phase difference between the two signals and you look at the intervals where the space is constant, more or less, where the phase difference is constant, and this length is greater than statistically expected length, because right, then you can postulate or you can hypothesize that indeed this is something anomalous and also in not coming just from the random behavior, but rather some direct behavior and some interesting phenomena, for instance, indication in the wrong sides, neuron conditions. Okay, so okay, yeah. So then, if you do it mathematically, you can. Again, if you find it very simple, I'm sorry, because I've given talks to very diverse population of people usually have. It's very difficult to balance between the detail, level of details, complexity, and intuition. And therefore, if you go into much more detailed things, but so far, this way. Okay, so that if you take the Hilbert transfer of one signal, one population, this guy, another, this guy, then if you multiply this by its conjugate, well, and the second one, by the conjugate, complex conjugate, the second one, you get something like this, and then you compute the expectation over. We'll talk about over what in the next slide. If you compute the expectation, you see on average how this product behaves, and if it turns out that these vectors point into more or less the same direction, then after averaging, you get the length of this vector, which is significant from zero, the red vector, and therefore you can state that, well, yeah, there is some phase on more or less constant phase difference. On the contrary, if you don't have this, if vectors point in all different directions, after averaging the black vectors, you get the red one, which is relatively small, and then you can say, well, this idea is reminiscent of the phase working value, but I'm not exactly talking about this now. I just want to do some intuition behind this. Okay, so then there is this method called coherence. Okay, I also call it coherence. Make mistakes later on correct the slides. Coherence is when you talk about complex part. Okay, the complex. Okay, so again, the two sources. We compute this expectation, which is cross-spectral coefficient in the previous slide, right? And then you normalize it by the power, by the instantaneous, by the average instantaneous power of your time series, okay? And coherence itself is complex value, okay? It's complex value. So if you have time series which are aligned exactly, that the coherence is exactly real. The coherence is exactly real. When they are shifted by pi over 2, for instance, okay, pi over 2, that the coherence is purely imaginary. Okay, this is important. You will see why. And so you can represent the coherence as a times sine plus b times sine. In effect, the square root of a squared plus b squared plus unity. So this batch is complex, and depending on the phase difference, which you see, the magnitude of the current will be computed to by either real part or imaginary part or by both. Okay, when the shift is by 4, for instance, then both of them will continue. Okay, so why? Okay, how we compute the difference, how we do the average and stuff. Okay, if you talk about spontaneous difference, that they don't like data. Okay, and as we already see, this red and blue is your analytic signal. Okay, it's in one side and on the other side, two locations, for instance. Then you conjugate this guy. I can draw the conjugate, so red is the side, right? So then you multiply these two for each point, you get complex numbers and average over time over this time, okay? And then you get a single point, you get two numbers, the real and imaginary. Okay? Then you shift the reader and do the same. Okay? So this will be spontaneous coherence. Okay? If you want to quantify by a single number the amount of, well, let's say, crosstalk between two sides, right? Between communication, if you attribute this direct measurements can be coupled with coherence in direct measurements to the actual communication, then you can take the absolute value of this complex number and get some value, which some scalar, which will tell you about the extent to which the two regions communicate. Okay, so this is pure analytic values. So the evoked coherency, okay, that's another creature, but a very interesting one. Okay, the evoked coherency is you're back to the evoked paradigm where you present the stimuli every time. So each of this window, it is a line, is a stimulus presented, some picture or something that tactile stimulation already mentioned, and then you cut them, you align them. Of course, you do the compute the Hilbert transform of this. You narrow the filter inferential interesting. You compute the Hilbert transform, and then when you compute the average, you take this complex number, multiply by in one location, multiply by a conjugate complex number in this other location. But for this type moment, okay, with respect to the stimulus onset, with respect to the beginning of this trial, delta fold trials, okay, and then you average this complex coefficient across trials. So basically, you're trying to see whether or not, when the task has been started, whether or not the phase difference, the phase difference between the two activities in the population is more or less constant with respect to the beginning of the with respect to the beginning of each trial. Okay, so that you can get a picture coherence like this, but this one is the time within trial. Okay, and you can see evolution of this coherency within trial as a result of average. Okay, so of course you believe here that things are more or less stereotypic from trial to trial, and of course to do it like super properly, you probably need to cluster trials because some trials like you can move everything. Okay? If I see them finger outside, if I keep doing the finger here, you can almost nothing, you know. But if I remember that, by the way, I have to hold my finger, then since we like here again, and I will reinforce my finger, and therefore if I clearly two different types of response where I'm moving since unconsciously and unconsciously, but not since consciously. Okay? Therefore, there was a lot of underwater stories here, of course, but I'm just trying to. So, if you again just doing invasive stuff, since doing invasive with these people is difficult, actually good, but that's the study by Magellan. Where he nicely doing nature neuroscience, where he shows, for instance, the coupling between the visual and motor cortex of the cat when she is waiting, or when she is waiting for the movement, before the movement and after actually the movement has started. Okay, so you see very nice coupling between the brain science. Okay. And in case where she needs to stay and not to move, then you don't get this increase. Okay? Which is showing that this network is dynamically organized and to support the movement. It actually, when it says support the movement, it's not necessarily to initiate the movement. It may precede the result of this movement. It's a cascade of very, very complex things happening in the brain, of course. But one thing that I also believe in is that this whole thing is actually can actually be characterized by the networks. Okay, therefore, we're looking into networks, and therefore, school is looking into networks. Okay, now that was simple. Well, the rest is also simple, but that was trivial. So the other stuff with this. Now we even want to measure the activity without penetrating the brain, without faults, without plants and breeds, without plants and animals, stuff like that. Okay, so to do that, because it's in humans, and because MEG, magnetoencephalography, which actually is registering the magnetic fields produced by those current dipoles that were and this is a picture from CTF website. CTF, I don't know what I just mentioned. It's a company that produces equipment. Okay, so the dipoles generate the magnetic field. This magnetic field is measured by the sensors located in proximity of the head. And the standard technology is to use squid-based systems, superconductive quantum interference devices-based systems, that have magnetometers submerged into the liquid helium in order to maintain the superconductive state. Okay? But modern technology based on optically balanced magnetometers is using completely different principle, more like the resonance principle, but with the cells of the let's say rubidium vapor. Well, I will talk to 3 days. Aspect. Okay, but anyway, so the measure magnetic field, the bad thing about magnetic field is that it decays very fast. Therefore, these sensors, which are located quite far away from the brain still, because the wall of your vessel is about 2 centimeters, maybe 2.5 centimeters, depending on the location. And the distance to the source may be as large as the superficial source in the brain, maybe as large as 5 centimeters, which makes the signals that we register very weak. Okay, so the human evoked response is an order of 10 minus 13 Tesla, and the Earth field is 10 minus 4, just to get to 8 or 9 orders of magnitude. And if we talk about oscillations, that they're more powerful, but still very weak. Therefore, to measure the whole thing, we need to do a so-called magnetic field, which is actually not that easy to buy, not because of money, because of other reasons. Okay, so but good thing about magnetic field, unlike the electric field and the EEG signal, the magnetic fields outside the brain are very nicely modeled with electromagnetic model in a way that we can have quite accurate model of the signals that we observe outside, given that we place a dipole in specific brain region. Okay, and these fields that we observe do not depend on the local conductivity or local conductive profiles. Okay, this is just physical stuff. This is not and therefore, because this forward model, which predicts the signals that we measure inside the brain, outside the brain, due to activity inside the brain, because this forward model is accurate, then the inverse model is accurate enough as well. And this allows for very high spatial resolution that I mentioned in the beginning. Okay, but the important thing about it is that it decays very fast. Okay, so this is how it looks. This is the neural system that we have in Moscow, in the Moscow State Psychopedagog Institute of Psychology and Pedagogics, and this is the CTF system, and this is Nikita, wherein there's OPM sensors, which is blue word in the MEG method. It allows mobile subject to move, and we have just recently published just out in human brain paper another magnetometer based on flux gate principle together with Russian quantum center and Sculpture. We published a paper where we explore the use of this magnetometer, which is very simple, much simpler. This one also works without helium or anything, and can be placed very close to the head, and we register magnetic fields with the sensor to I4. Yes. Okay, is it okay? It's better? Yeah. Okay. In a specific brain region. Therefore, we need some tools to go from the sensors into the sources, okay, to the source space. Okay, what is source space? Well, source space, you can define it differently. You can say, for instance, that the source space is you take your MRI of the subject, MRI volume, that process it and extract, it can be even done automatically, and extract the cortical surface, cortical manifold, this actually fine surface here, the cortical surface is smoother. Okay, so, and you can place at each node of the surface, which is partly defined by these triangles, you can place a dipole and say, well, this is my source. Okay, so this whole bunch of the sources is giving rise to the data that you get. Okay, this is how we model it. And you can avoid extracting the cortex, and you can simply take the MRI volume and assign a grid to this MRI volume and an initialization to the dipole. You know, the good thing about extracting the cortex, if you can afford doing it at very high resolution, that you can fix the orientation of the dipole, right? Because dipoles are vectors, and so it can be oriented differently. And if you know the cortical curvature, that because of anatomy, the dipoles are oriented orthogonally to the cortical surface, and therefore it can by the factor of, in MEG by the factor of 2, and when the reasons why, is a huge number of non-sources. Okay. Okay, so the whole thing is based on the assumption, is that actually quite reasonable assumption, that you can model the head as one conductor with a set of Maxwell equations with quasi-static approximation of Maxwell equations, and actually given an allocation of the brain, you know, so application, you can create this one, right? You can create a vector. You can create a vector which tells you how the source is seen by the sensors. Okay, you can also visualize this vector using what we call topography. Okay, basically the color encodes the intensity as a magnitude of the the actual coefficient. You can put it in negative, but it tells you if this dipole is active with subunit activity. You know, yes, with subunit activation, that what will be the signal outside that you see. Okay, and of course, because there are many of such dipoles, you know, this matrix is called for model matrix or gate matrix. Therefore, will denote it as G. For some intuition, if you talk about EEG, electroencephalography, we measure the voltage, and if you talk about dipoles, if you assume that we talk about current, right, not the dipole, current, but just current, that the units of G is apparently ohms, right? Because you take current, you multiply by R by ohms, and that voltage, right? So the reason I'm saying is because when I was teaching at State University at some point, the biologist asked me, okay, what is the units of G? And I thought, well, this is a great question because it really adds a little bit, but still adds intuition to what this whole thing is. All this is just ohm to ohm, nothing more. Well, it's limited, complicated, and blah, 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 but conceptually it's just off to off in EEG. In MEG, well, it's magnetic field, so you can also introduce some potential, blah, 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 and do something. But that's so that you have this matrix and you have a magnetic model that for each location R and for each rotation of the dipole allows for creation of G, which is a vector, which is a set of coefficients, which describe to you how the source is backed onto the sensors. Okay. Now, one is that it's important to understand that this model is instantaneous. So it's not like sound, like where you have sensors, you have sound wave coming. This sensor, this wave comes first, and this sensor, this wave comes last, right? So no, it's not like this. Everything is instantaneous, but different for different sensor. But as soon as dipole is on, these sensors assume this activation immediately. Okay, it can positive and negative. It may have it has literally some spatial pattern, and these patterns allow for actually telling where the sensor, where the source is coming from. Okay, where the source is sitting, right? By so-called inverse problem. Okay, so but just for the mathematical formulation of the forward problem is that your measurement vector x of t. I try to stick, not everywhere, and I try to stick to notation that vectors are all columns and vectors are denoted by small letters, small bold letters, not italic. Okay, matrices are capital bold letters. Okay, So therefore, we have mesh vector of measurements of each time instance T, right, by these tensors. Is a linear combination of columns of the forward matrix with elements from vector S, which here, sorry to state because of the S, the S sub I, right? Sorry, I was fixing it, but it didn't fix everything. Okay, so it has to be S sub I. So at each time instance, we get a linear combination of columns of G sub I of this forward matrix with coefficients that correspond to the activation of populations, okay, neuronal populations, okay. And then, of course, we have error term, where error term can be anything we don't explain. Error term can be something which comes from accuracies of modeling of the forward modeling, and so error term may be something which is not interested, and we are looking into beta band, and we get alpha selection as well, where alpha is noise. Okay. So, and of course, the noise can have very complex spatial structure. Okay. So we are not assuming noise as well. Okay. So now, how do we go from sensors to the sources? Okay. Well, there are at least two ways to do it. Okay? In fact, there was a platform job, but the general idea is that once you have measurements and you have your forward model, you usually have you either have an average forward model for subjects in some logical brain, or you have individual head model from extracted from the MRI of each individual subject, and then we need to solve this, and we need to find S, which will minimize this guy. Okay. The problem is that we have about 200 sensors and about, well, in ideal world, about 300,000 sources, okay? 300,000 dipoles, 300,000 nodes. So the problem is severely underdetermined, just hugely underdetermined. Therefore, you need to employ the theory of solving the ill-posed problems, okay? And you need to recognize this inverse, this different methods, okay? There are other approaches which say, well, not actually everything is that, okay? There is some application to that, okay? One or two, or maybe three, maybe five, okay? But not more, okay? Very few. All we need to do is to find these locations and not the problem stop the problems, apparently. But it's still a painful process because you can't change the world. Because you don't know how many sources are there, and you don't know its application for the source. In order to find its application for the sources, you need to perform ongoing research, which is a function. If you know that the dipole is a single dipole that you quantums, and it's active, that problem is simple, so the problem is actually trivial. Okay, but if you have multiple dipoles, things become much more complicated because of things I mentioned. Okay, so and then you need to do dipole scan and nonlinear optimization. So you can basically measure if you get data, you can basically check how let's say this topography, okay, that you see, how well it matches with each of these vectors corresponding to the topographies of different sources. You can compute the cosine between that, for instance. And then say that, okay, here the cosine is the largest, therefore I believe that this, but this only works if you have a single source or the sources produce topographies which are not reducing of each other, okay, they're far away, right? And they don't overlap, and then you can do it efficiently. There are other methods how you can do it. The reason for this slide is actually to show that this is the standard observation model for the MEG or EEG data, and a lot of methods have been developed to solve it. And we also contributed to it, but a lot of different methods. And one of the things that's been used here is that in order to solve this, you need to introduce priors, and you can do this in a very nice way using the standard data framework with either Gaussian or non-Gaussian priors, distributions. But the theory is well developed. So remember the situation, okay, please. So, okay. So this is how you do it with Bayesian inverse, right? If you assume that things are Gaussian, if you model the data as Gaussian, and your source space is Gaussian, the data is Gaussian, then your solving the inverse problem basically boils down to the minimization of this functional, but this guy reflects the prior on the sources, and this guy reflects the data feed. Okay, so there are two extremes. Okay, one extreme you can say, well, I don't have any prior. Well, if you don't have any prior, you have to have that solution. Well, the other thing is that you can say that, well, I don't have the data. I have only prior. That's also great because you get trivial solution. You can have a nice data. But the truth is somewhere in between. And the tune by the so-called regularization parameter, which allows you to balance between the data and the prior. Okay? The prior is something that you can bring to the data. This is the knowledge that you can, for example, say that, okay, well, because of my spatial relation, and because of my need that I have, like, let's say, ability, for instance, I expect that the groups of activity will go on the order of several points, okay? And it has to be smooth on the scale of several spatial points, right? Or you can say, for instance, well, I believe that my activity is changing in time relatively slowly, again, because I don't have access to individual neurons, but I have access to the activity of populations, and of course, you have jitter and those potentials, and then the average, you don't see the spikes, but you get something much slower, right? And again, depending on the oscillation, for instance, the frequency, you are making for all frequencies, you might have larger extent of sources. For high frequencies, you can have more complex sources, right? Those are the things that you can incorporate with prior. You can also say that, for instance, you want maximal smooth maps. For instance, you want to make no assumptions as deep as possible, then you can make maximal smooth maps. So this is so-called low resolution electromagnetic tomography by Pascal Marquis. Or you can say, for instance, you want focal solutions. You can have several dipoles, several regions activated, but those are few and they're very sparse. Okay? All this is regulated by the prior. Okay? How to derive the prior? You can derive prior from the data, and that will allow into the variational Bayesian methods, which are complex but very powerful. But you have to be careful because if you derive your prior from the data, then you're in circles, and you better add some structure to your prior, and then inform the structure of previous knowledge and already state specific values from the data. Okay, but this way or another, if you in a simple case, the inverse managed just by simple multiplication by matrix W, and this matrix, because if you solve this, you get the closed solution, and this matrix W is simply matrix. Okay, you just simply take this matrix and the matrix has rows, right? You multiply the row at each time slice. Here are the channels, right? Click it. Right? So the channels, you multiply your data by this weight vector. So basically, sum these lines, these coefficients, they're the same coefficient for each time slice. In this case, and you get for each time slice, you basically for each row, you get each pixel, you get one pixel here. Okay, so you have many rows, then you get this sliced version of the frame, which shows the activation during the presentation of the output. Okay, so again, the point here is to show that solving the inverse is a relatively well-established approach in MEG, and can be handled quite nicely, actually, quite sufficiently accurately with simple methods. Okay, with simple linear methods. Okay, of course, I'm not saying that it's not necessary to develop something more advanced, but the inverse methods based on this Bayesian and even Gaussian Bayesian approach, these Gaussian approximation of distributions works actually quite well. Okay, and so-called norm estimation, that is the name somehow it was coined for this method, is actually the most widely used method in solving the inverse problem. Okay, so like for instance, you can if you do since with priors and dynamic priors over time in the iterate, and you have multiple subjects and try to bring information from multiple subjects, assuming that your different subjects have more or less the same activity, but maybe activities like differently, and plus the subjects may have some individual activity. You can leverage this nicely with the so-called Gala framework, group analysis with accuracy. You work with Vladimir Kozlov back in 2015. It shows very nice differential response when you present this kind of phase. And Campbell phase shows very nice regions in the vector pathway, visual pathway, and each region, of course, is served by the time series. And the blue one in one condition, and the red one in the two-phase condition. So this is just to give you a flavor example of what you can achieve. Okay. All right. So that was that we were talking about the steep source model, right? Now talking very briefly about the dipole form model, right? That dipole focal source model. That we just simply fit dipoles. The simplest way to fit dipoles is again to find such RF data given the electromagnetic model that minimize the difference between the data and your synthetic data which you want. Okay, and you can fit dipole, and then you can, once you found the dipole, you can estimate the time series by multiplying the data, multiplying the data by the transpose of the topography of the dipole that you find. Okay, of course there are better ways like inform or some things, but those are conceptually similar in the sense that it's all achieved by singular. How to find the vector? Well, this is another story. Okay, so this is an example of how you actually do this informer. You can pinpoint the location, and you can then design a filter in a smart way so that you can extract the activity of the source, and then you're interested in but we are not interested in this. We are interested in not pointing the sources, but we are interested in looking at the sources and looking for networks, but using the techniques similar to those we use when we infer sources. Okay, and how we infer sources we already usually more or less know now. Okay. All right. So let me see. Yeah. So if you want to non-invasively look for the networks, we have difficulty. Okay, difficulty is linked to the fact that if you consider two brain regions, okay, and these two brain regions produce certain equations, and they have correspond zero zones G sub I coefficients, right? They will both map to this central location, and they map to this central location, right? Therefore, if you try to measure some coherency between them, because of this mixture, right? Because each of the sensors will contain a mixture of activity of sources, of these two sources, you will get spurious coherency, not because they're talking to each other, but because of this so-called quality conduction phenomenon or field spread, if you talk about APG. Because a single sensor is measuring activity of all sources, well, there's different extent, right? But still applying different sources, okay? So, and if you have, of course, more sources, then more and more formal signal is measured by the sensors, and then for using simple measures, just like correlation curves, like for coherency of the sensor, simply not work. Okay, there have been quite a significant effort during the end of last century on this, when people developed techniques to battle this volume reduction, okay, not to ignore, okay, somehow. And they succeeded to a certain extent, but they all still talk about the two-step procedure. Okay, they first say that okay, we do it a very specific way. We solve the inverse problem. We try to additionally battle the volume conduction, and then take the source of activity and measure our networks. Okay. Oops. That's right. Okay, good. Okay, so yeah. So for one is a I'm going to show you this slide first, right? Yeah. Okay. So this one thing. When I will show you in details in the next two slides, but in order to get rid of what production, they are focusing on the imaginary part of the coherency, okay? Because I will show you the imaginary part of coherency does not depend on volume conduction, okay? Because the imaginary part of the coherency has the real part, the imaginary part, and imaginary does not depend on volume conduction, but the real part has volume conduction and the true coupling information. So we throw away this true coupling information, which is informative if you want to talk about networks with small delay activity, okay? Because the networks they're delayed by pi over 2, no, then the imaginary part is ideal to measure that. But if you take if you talk about the zero phase coupled networks or networks with small phase, that imaginary part has very big signal, remember, because it changes the cosine and sine, right? And therefore, it's not an ideal vehicle to carry this information about this coupling onto the sensors, okay? And actually, zero-phase coupler is present in brain data. Multiple examples of it. Very few of them here. And the mechanisms, it can be either bidirectional coupling, or it can be from source, of course, which is less interesting. But still, if the source, one source is not visible by the modality, then the best you can do is just use them. So you communicate with each other, and then infer from previous data with prior knowledge that perhaps it's due to some common drive, right? And it has been also ubiquitous in gamma oscillations analysis, but not phase methods don't seem to phase coupling. Okay, here's the reason why. Because before we understand why the non-invasive imaging cannot see traditionally cannot see close to zero coupling, we need to go to this little bit of maths. Okay, very simple again with vectors, multiplication of vectors by vectors, scalars, and cross-spectral matrices. That's it. Cross-spectral matrix is just simplification of coefficients. Okay, that's it. All right. So now your data, it's okay. I mean, many questions. We are okay, we're on time, so we have 30 minutes, so I can answer questions. Yeah, but the approach, because I
excuse me, I'm a little bit wondered how is spatial leakage effect affecting the phase of the signal, not the amplitude.
Because things are instantaneous, the forward matrix is just coefficients. Okay, they're not complex numbers. Therefore, we assume that spatial leakage is not affecting the phase. It's just mixing the sequence. And of course, when they're mixed, you have difficulty in estimating the phase. But there is no, as I said, there is no thing like in acoustics, for instance, right? Or optics, right? Where you look like you have very high frequency, very small distances, super small distances. But you have phase information that to one sensor arrives earlier than to another. Here, we don't have it. When source from the source space to the sensors, we assume that there are no delays. And if you solve these equations, there is a paper I can refer to, but they show that spatial scale of, if you talk about hyperspectivity, if you talk about the conductivities, like specific conductivity which you have on the brain, then the spatial scale is about 65 meters. So your hand, single point, 65 meters. So phases are not playing a role here. However, if we somehow find super high frequency oscillations like 1,000 hertz oscillations and make systems which can see them, a little bit of phase. I think there was a discussion on Facebook. We discussed shifting very little, like about 2 or 3 or 5 degrees of phase will accumulate, and this may give additional information to solve the problem. But this yeah, but it's a good question because of course the phase difference would add information. Okay. So now consider the toy system. Now we have only 2 sources and we have only 2 sensors. Okay, so those are your measurements, and it's the summations of G sub I and sub I. Now it's just simply G1 times S1 T, G2 times S2. Okay, then do some time frequency transform. You can actually do it differently. You can do wavelets, you can do fit your data, as I mentioned, in some frequency range, and then we Hilbert transform, right, as we did. But the bottom line is that you get some complex coefficient. Then, of course, this transform is linear, therefore, all the amplitude maintains, is retained, and you transform everything, right? You transform the data, you get the noise, your source, you assume you transform them, because you don't have access to them, but just simply take the short-term Fourier transform, this, for example, or wavelet, or as I said, the Hilbert transform, and you got the guy who's modeling this, okay? And then you compute the cross-spectral matrix, okay, which is simply expectation of x times x initial, which is one vector times another vector conjugate, and then we simply average of times, or you average over some time. Okay? So that you get this back, and we will now look at the model. Okay, what this guy, how this guy is expressed by the topography of source, because this is what we're interested in what to solve the inverse problem in this respect. to already not sources, but with respect to the coupling, to the methods of coupling in the source space, okay, to the network basically, okay. So here again, this right. So your matrix SXX, SXX of T, is your cross-spectral matrix. We assume F part, right, that represents stimuli. In 2x2 case, you will have a 2x2 matrix because you have the two sensors, and this matrix will have different values for each time slice. Okay, and we can call it the tensor, you know, so that each time slice is the matrix. Then you have many time slices, right? And the number of time slices is equal to the, if you look at the trial, F paradigm, then it's equal to the number of trials, or to the number of time slices within trial, which is usually, I don't know, like 1,500. Okay, so now if you simply substitute these guys into this expression, you arrive to the following model to the cross spectrum. Okay, well, that's already become more or less interesting. Okay, because then you have three components to it. Okay, the first component, the one that's been ubiquitously used, is the symmetry component of the cross spectrum, and coherency derived from the imaginary part of the coherence, basically, of coherency, which is only modulated by the coefficient of coupling, by the source space coefficient of coupling, okay, because S12 is basically the cross-spectral coefficient, but in the source level, in the source space, okay? Is it okay? You follow? Okay, so, but if you look into this real component, you have two parts to it. The first part is modulated by the real part of the source space cross-spectral coefficient, okay? And this is the vector or the matrix that carries information about it, okay? Like once you see this matrix, for instance, somehow in the data, you know that source 1 and source 2 are coupled, and they are coupled, primarily the real part is contributed to this coupling, but means that they're coupled with zero phase or close to zero phase, right? And then you have this other part, but it's also real, but it depends only on the variance of sources, okay? S11 and S22 is the variance of sources, basically the strength of sources, okay? And this guy is pretty strong. It really contaminates the measurements very badly. And should you get rid of it sometime, and to get access to the pure data which are modulated by real and measuring part of the source space couplet, right? Information. That we can do quite well, because this will be a linear equation, and you can then look for these guys, okay, in the static methods. Yeah, look, it's just the beginning of the okay, now this is just a repetition of the whole thing, right? So I mentioned it's important, and this is basically volume conduction. What's important here is that the G1, G2 transpose, it's a matrix, right? So it's a matrix you can see. I mean, it's a shape, right? And this shape is different for the couplet, so, and for the conduction from sources, right? It's different. Therefore, you can somehow distinguish between these two if you consider the activity of several sensors, not a single sensor. If you look at the sensors, you can distinguish, they're all mixed. But because they have different right? Okay, now go to examples already grown up. So no to example anymore. The full blown model is this, but exactly the same thing, except that we have L sources. Okay? Same thing. So you get real component of which is split by the volume conduction and the true real couplet, real zero phase couplet, and you have imaginary component. See, this is important. If you why the imaginary component is not characterizing the coupler? Well, it's very simple. If your sources are the same location, right? Two sources, that's basically a single source, and this is what will generate the volume conduction. So if you make I equal to G, then clearly this guy is zero, right? And if this guy is zero, that means that volume conduction is not reflected into the imaginary part. So therefore, people are using it, but we decided to get rid of it, okay, somehow. Okay, how we do it? Well, very simple. We take the matrix. This is the matrix, okay? We take the matrix and vectorize it. Okay, so it's built by rows and spectral. You have by matrix and okay, and then you in the model you of course vectorize your products. You can do it either this way or you can do the chronicle product, right? And then your model is simply a linear model which shows that the cross-spectral coefficient is a linear combination of these guys, and of these guys, and for some else. Should remind you. Just linear combination. Now, this guy is very bad. Okay? Yeah, basically, this is how vectorization works, right? So for each time slice, you have matrices, then you vectorize it, and now you have a single matrix where this dimension, I just left several sensors here. This dimension has square, right? So each of these guys. So, well, this guy is pretty bad. Okay, it's very powerful. If you take this guy and measure its norm and do it for multiple locations, you just take two networks, one network with two locations here, like I and J, and compute this corresponding QI, which is GI parameter GJ plus, all these guys. Compute QI equals QIJ, QIJ minus QJ and QI, and you get this. This is volume conduction, okay? This is this guy. This is volume conduction from two sources. It's pretty high. It contributes a lot. And then this one is something that scaling the imaginary cross-spectral coefficient, and this one is which is scaling this one is scaling the real cross-spectral coefficient. Okay, so if you add this is shown as correlation coefficient because you can have different points, right? And each point is characterized by its topography, right? And you can plot it randomly. But I organized it as a function of the non-topography correlation coefficient, basically similarity of these two guys, right? If you take, for instance, these two topographies, that is with this point, because sorry, all right. This one is the activation on the right, this one is the activation on the left. So the topographies are nearly orthogonal, right? They put correlation between them zero, and in this case, the volume conduction effect is this strong, and real and imaginary part make it of two source space, not left, make it sensors with these kind of coefficients, with these kind of norms, which define the single measurement, right? Of your measurements with respect to the curves. Okay. So, and if you have this case, for example, where the topography is more or less overlap, then this corresponds to this point. The volume conduction is still pretty high, but the real part becomes more pronounced, and the imaginary part dies off because the topographies are similar, and sources are close to each other. Right? And the limit when they're in one point will go to the right? So, okay. Now, okay. So, just to reiterate, you can have this as you can consider this CXX your vector as represented by the real part and by the imaginary part, right? And the real part is split into the spatial leakage and some other component, right? Which is true cover, right? But it's not split orthogonally. The imaginary and real part are orthogonally split, but these two guys are not, and therefore you need to have some smart way of getting rid of this guy. Okay, well, but we have some interference and we have multiple measurements, vector of measurements. We use projections. We always use projections. Okay, projection is very simple. You find a subspace where the undesired guy lives and project the data away from this subspace. Okay, well, the subspace is different is given by these vectors QII, right? You can collect these QIIs over the entire frame. You can stack them in a matrix, and then you can find, because of course you don't have sort of how you say what you use it. But if you do SVD of it and try to concentrate the power of this volume conduction into the small number of components, you can actually can show that quite compactly and project your data away from the volume conduction. So here, this is the before projection thing, and this is after the projection thing. So see, the volume conduction is greatly suppressed. Of course, you affect the real component because that not in orthogonal the volume conduction and the real part of the cross spectrum in the sensors on the sensor level are not orthogonal. You affected them, but you can take this into account when you're modeling the solve the inverse. But you have greatly suppressed the volume conduction term. And the imaginary component is, of course, unaffected. Okay, it's like e to the power of x. It's a famous cycle for Markov from SU. Okay, but here it's no. Okay, so this is how this looks. And if you take a simple cross spectrum, the horizontal cross spectrum would look like this. If you take the absolute vectors, and then the projected cross spectrum looks like this. Okay, so one of the applications of this, even without going into the sensor spaces we're going to connect, even without going into the sensor space, you can use this projection to feed these guys to your machine learning solutions. Where you want, for example, to focus on networks, not in the powers, right? You can have, for instance, projected cross spectrum away from the volume conduction and cross spectrum projected into the volume conduction. You can have two guys. You can untrain the network with respect to the guy projected into the volume conduction. And you can train it with respect to the volume conduction. This way, you'll make sure that your machine learning solution is not tuned to the power of sources, but rather to the interaction. Okay, we don't do that, but we will at some point. Okay, so if you then, after the projection, the projected cross spectrum is denoted by the orthogonal sign here, and QID topographies, because we apply projection to them, but yourself when they have affected, is denoted by this guy. This is your equation, which is, of course, nobody limits you to put it in a simple sum, right? And introduce here index k, which is I times L plus j, right? And that's it, basically. This is a linear equation, but now each Cij is a two-node network. Okay, so you're no longer looking for sources, but you're looking for the networks, and you're looking for the networks after getting rid of the volume conduction term, and therefore you can be sensitive for and for real. I'm not going into this. I did some simulations. I just want to show this. Okay, explain details. Okay, so this is how you can you simulate networks. Okay, just randomly simulate networks, and you have networks being activated with time series which are shifted. You know, sometimes it was close to 0, sometimes it was close to 5 or 2, for different phase difference was different. Okay, and we keep like something that comes out not the trials. And if we used only the real part for the inference of the networks, and then clearly those networks which have delay of about 5 or 2, they take it very fully detected, right? And those networks, but if you use an imaginary part, then on the contrary, those networks which have low delay get fully detected, and those which have 5 or 2 delay get well detected, right? If you combine the two, you get this very nice static curve that shows more or less uniform performance with respect to the okay? Hence the fact that detection networks is neglected. I will skip this. This is studying the dependence of this whole thing on model accuracy. This is I will have to skip this. This is very nice work which was done by Dana Gage, my master thesis, where she basically looked into the situation because they are not using coherence because they stay in the legal framework. We can't do all these normalizations. Therefore, we use cross-spectral coefficients, and cross-spectral coefficients can be affected not only by coupling but also by the power of sources. Okay, and that's what developed a very nice statistical test that is both parametric and at the same time is informed by the data that allows you to exclude the networks, not two networks, but those which are spurious networks, which are explained by the powerful sources but not coupled sources. Okay, like for instance here, you can model against 3 networks like this, and then you can have one network which is false network, and then the test very nicely detects it. I'm not going into details of this, show you the application of this to some mental rotation data where you have a subject who was shown the stimuli, which was the drop 10, and he or she has to take this hand, brain, and say it's the left hand or it's the right, okay, and the orientation of what you're doing at the time. Okay, so we found networks which are, let's say, alpha band networks, such as batch that those are significant. But the beta-band network, and the gamma-band network were found to be significant, and they connect temporal pole and the motor region, and the temporal pole was left into the picture making. We did analysis, and I'm going to this. It's all written on the paper, which paper we justify the significance of these networks, and we can only ensure not only the networks, but also we can ensure the time series, okay, when the network is active. Okay? So of course this needs further work, and this is what Dasha is going to do. It will be it is basically supported by the idea fund, which I'm super grateful. Okay, and that's another application which I wanted to show you. This experiment by one people who accidentally died in July because of the crash of his bicycle, a motor scooter, and this was tremendous loss to neuroscience. But I hope it can continue to work. So his idea is that obviously was sleep theory. Okay, so that the brain, the regions of the brain which are involved in processing sensory information, where the data included in the brain, is switching the processing of information from the drugs, from our internal organs, from this level. Okay, this is a fantastic theory. I believe explains many things, and there are several papers published on this. But it's not yet accepted in the psychology community. Everybody hates it. Everybody, because it breaks many things for them. And so, but he conducted two experiments. The first experiment he conducted himself with multiple stages, like the Pedagogical University. They collected energy data with the tablet. The subject has swollen the tablet. The tablet was it's so-called Kremlin tablet. Okay, it was generating the pulses and was stimulating the guts. Okay, in the blue guts. And the subject was either sleeping or not sleeping. And we processed this data. We isolated fast sleep, slow sleep, and wake sleep, and we looked at first evoked responses, and we found fantastic evoked response in the insula, the region of the brain, which is known to be represented the internal organs during the slow sleep. And we also found the response in the occipital region, but later, just before spike stimulation, something like anticipatory response. Okay, those are just evoked responses for single analysis. Okay, and we found in cats exactly these two regions, and specifically the occipital region, which was also seen as highlighted in cats when they sleep in baby. Okay, so and I have to say that he loves his cats. None of the cats were sacrificed. The experiment, he was never confident in the name, in numbers. He was never, and he was then given them to people because the cats were very nice, because they were learned to interact with people, and also they were learned to sleep as soon as otherwise. It's very nice. Okay, so then we also found the induced beta activity response again just prior to the stimulus, like, and this amount is response is growing as you go into the study, into the experiment, so the brain is learning. And Dasha has just applied our method for zero-phase couplet and found this couplet in the beta region, which shows, and then another network in the beta region which connects some, so make it to insula actually, and the occipital region. This approach that I just described. So, okay, this is very clear, and just got to help okay, so we have 10 minutes. I will show you the perspectives. Okay? Because so far, the version of the cross-spectrum was very simple, which I did discussing with respect to GI, GJ topography, and that's it. But it's possible to do much better. It's possible to, for example, model this, take the source model as the source network model, okay, and then do some regularization on the top of it. For example, you can do a regularization, you can do a norm, get sparse networks, or you can do fractional norm. The fractional norm is important and interesting because of this. Because you can, okay, this is just from the system, therefore X is M, the rest is okay. So if you do, because if you talk about networks, and if you get the knowledge about the spatial resolution that we have and the temporal resolution, then we are likely to expect smooth activity in time and sparse in space. Okay, because our spatial resolution is limited, and therefore we want to pinpoint locations in space which are relatively far away, but those which are close to each other probably belong to the same population. Okay, so That you can use a mixed norm, which will be sparse in space, so it will be L1 or L.5, and will be smooth in time, which will be L squared norm, and it allows for very nice formulation because you can replace this intractable norm. It's very difficult to optimize. You can assume that from these iterations you move not far away, and then you can represent the square root as a ratio of the Frobenius norm by the square root of the source, which you know already at the previous state from the previous step of iteration, at the previous state of iteration. And so you can approximate this and then iterate, and it works very nicely. So far, it's only just in simulations. Those are networks and those are the activity profiles. Okay, you can see that we very nicely recover orbital and time networks. And of course, you can also go further. This is what Nasha is going to do. You can use spatial primers derived from the Magnetoencephalography region. You can derive primers from that and use either one norm, so norm approaches to inform the inverse of this network. Okay? So, and the last one, very on this last one, you can also take into account the dynamics of networks, because as you know that networks are switching between each other. That was a very interesting paper by Adam Baker back in 2014, and he received the BIPAC award for the Outstanding Research Award, where he shows that different networks, different standard networks, have a tendency to switch between each other, and they have very specific patterns of switching. Okay, and it shows that if you look at this as a graph, you can show that there is no path from, well, first it's all statistical, right? But there is no path from one network to another network, and necessarily has to be switched through, let's say, network A, B, and C. It has to go first to B and C, and can then go from A to C. And this actually is very informative, and obviously live, well, live, but that was just not live now, but still, it's very inspiring stuff. So cited many times. So this thing can be taken into account as prior to magnetic prior. Okay? So, well, I will conclude then. So I've shown how you can, it's actually for the first time, how you can measure zero phase coupling of induced activity with non-invasive measurements. So basically, we looked at cross-spectral, we freed it from the volume conduction by the projection operation, and that cuts the network protection task as simply a source estimation task, basically, but the sources are networks, and right in the top, the pairwise networks. And you can also apply a plethora of networks that you can detect one network. You can project your vector, the data, away from this first network, and you will not use other networks which are going from one of these nodes, right? Because you can only pick, on one or on the two nodes, but after the projection, you can still have a network which originates in one of the nodes that you remove, but with respect to some other network. Okay, so this is potentially the thing which slows this thing is that it's relatively slow and cumbersome to do this computation because the dimensions are relatively large, but it's not really a problem with computational power. So, and again, the papers that are published, you can read them, and there are two papers that describe this approach. And that's it. Thank you.